In this video, I'm going to show you how to solve the ALEKS problem called calculating the reaction rate of one reactant from that of another. Buckle up because this problem is pretty tricky. So just like the title says, it's going to be giving us information about the rate of reaction for one particular molecule, and we're being asked to calculate the rate of reaction for another molecule, but it's not that straightforward. The very first thing that we're going to need to do is dig through all of these words and find the chemical reaction that's actually taking place, write out an equation, and balance it. And so this is telling us in this reaction, gaseous ammonia reacts with dioxygen gas to produce nitrogen monoxide gas and water. There's our chemical reaction. If you're not familiar with the formulas for anything that's in these words, just look it up, like just Google what ammonia is, and it's going to be super important that you get these formulas correct. You're not going to be able to balance the equation if the formulas are wrong. Ammonia is NH3. We do not need to worry about if it's gas or liquid or whatever. That's not important in kinetics. So we have NH3 reacting with dioxygen gas, that's going to be O2, to produce nitrogen monoxide, that's going to be NO, and water, H2O. So there's our equation, and we need to balance that equation. And the nitrogens are balanced. Hydrogen, we have 3 versus 2. So I'll put a 3 here and a 2 here. And oxygen, we have 2 versus... now my nitrogens are not balanced. Okay, so put a 2 here for my nitrogen. So I have 2 nitrogen, I have 6 hydrogen, and I have 2 oxygen versus 5, of course. Making the problem even trickier, when we get into a situation like that, we just need to double all of our existing coefficients. Okay, so now double check. 4 nitrogens, 12 hydrogens, 10 oxygen, 10 oxygen. So there's our balanced equation. The next thing that we need to do is figure out which 2 molecules we're going to be working with in this equation. In this problem, it's going to be giving us the rate of one molecule and asking us to calculate the rate of another molecule. So it looks like it's asking us to calculate the rate at which nitrogen monoxide is being produced. So that's this guy right here. I'm just going to highlight it. This is one of the molecules we're working with. And then it says 114 liters per second of dioxygen are being consumed. So that's the other molecule right there. So we have to find, just from the words, there's a lot of words in this problem, one molecule, it's going to tell you the rate, and it's going to have it in disguise, like 114 liters per second are being consumed. So this is the one that we know the rate, and then calculate the rate at which nitrogen monoxide is being produced. And that means that we can effectively ignore the other 2 molecules in this equation. So we can really just focus on these 2. The next thing that we want to do from these 2 guys is write out a relationship between the rate of the rate of the consumption of O2 and the rate of the production of NO. To write this relationship out, we're going to need to use the stoichiometric coefficients. 1/5 because O2 has a coefficient of 5. 1/5 times the change in concentration of O2 over the change in time. That is equal to 1/4 change in concentration of NO over the change in time. And technically there's a negative sign in the front of anything that would be a reactant, but it's not going to be necessary for us to have that negative sign there mathematically. In this problem, everything is just going to be positive. So again, we want to use the stoichiometric coefficient in the form of a fraction in front of each one of these things. This gives us the relationship between the rate of O2 and the rate of the NO. And this problem is asking us to calculate the rate for NO. So that means this is what we're trying to calculate right here, just this part right here. And so what I'm going to do is I'm going to multiply both sides by 4. So that I can cancel out this 1/4 term right there. And now I have isolated what I'm actually trying to solve for, which I'm going to rewrite that down here. So what I'm trying to solve for, the change in concentration of NO over the change in time, that's what's actually going to end up going up into this box right here, is going to be 4/5 times the change in the concentration of O2 over the change in time. 4/5 I got from just combining that. And the change in concentration of O2 is up here in the problem. Now, ALEKS couldn't just tell us the change in concentration of O2. That would be too easy. Instead, it gives us a bunch of information that we have to use to calculate this. So it's telling us that we have 114 liters per second. That's giving us a volume. It's giving us the temperature of a reaction. It's giving us a pressure. This starts to look like a gas law problem, PV equals nRT. It's not giving us a molarity, which is what we need to be putting into this box right here. So we actually have to calculate, using the ideal gas law, calculate the number of moles of dioxygen that are being reacted here. Again, using the ideal gas law. So if we're going to use the ideal gas law, we're going to solve for N. N equals PV over RT. And I'm just going to do that down here. The pressure is 0.55. I'm going to leave those units off to save space, 0.55 atmosphere. The volume is 114 liters per second. Make sure that you're getting everything in the right unit. The pressure has to be in atmospheres. The volume has to be in liters. The temperature... R is next, 0.0, that's our constant, 0.08206 liters atmospheres mole Kelvin. The temperature has to be in Kelvin, it's in Celsius, so 257 plus 273 is 530 Kelvin. And again, I've left the units off down here just to save space, because when we put the units on, it makes it way bigger. So let's solve for N, 0.08206, 530. N is 1.44 moles of O2. Technically, this is supposed to be in units of molarity, but it will be okay if we just use units of moles instead of molarity. Remember, molarity is moles per liter. Just having the moles is close enough to molarity. So let's go ahead and fill this in. 4/5 times the change in O2. That's going to be 1.44 moles per, it says per second. So that's our time per 1 second. We can work the math out on this. 4 times 1.44 divided by 5. We get a rate of 1.15 moles per second. This is what we've solved here. This is the rate of NO, change in concentration of NO over time, per time, 1.15 moles per second. So that's kind of the answer to this question, but ALEKS can't even make it that easy because it doesn't want us to express our answer in units of moles or even give us an option of how to express our units. It specifically wants our units in kilograms per second. So the next thing that we have to do is a mole to, not just gram, but mole to kilogram conversion. 1 mole of NO. So when we do this conversion, we're just going to be paying attention to what the molecular formula is here. 1 mole of NO is 30 grams, 14 for the nitrogen and 16 for the oxygen. 30 grams of NO. That lets our mole units cancel, and that's going to give us 34.60 grams per second of NO. And then we're going to do a gram to kilogram conversion. 1,000 grams is 1 kilogram. And we get, finally, the answer, 0.035 kilograms per second.